Practice problems verifying trig identities and solving trig equations. This video will help you refine your skills verifying identities and also solve more complicated equations containing trigonometric functions. So this video is good after you've had some basic practice, some instruction on this thing, and now we're just kind of going back to review this a little bit and also kind of refine our skills a little bit. So if that's the situation, this video is the spot for you. Okay, so what we're going to do is we're going to alternate between verifying an identity and then solve an equation. I think skipping back and forth helps you kind of have to reset your thinking. It's a good way to practice. Okay, so we're going to start here, question 1. And we're going to verify the cosecant times the tangent of x is equal to the secant of x. And what I'm going to do in my answer here is I'm going to work the left side to look like the right side. So why don't you go ahead now and pause your video player and give this one a shot. So working the left side of the problem here, we're going to turn cosecant into 1 over sine of x, tangent into sine over cosine, and then you can see the sine of x dividing out. We get 1 over cosine of x, which then is the secant of x. Okay, next problem, we're solving an equation now, and we want to find all the solutions here. And notice there are no boundaries on the domain here, so we're not restricted between 0 and 2 pi. So we want to make sure when we find our spots on the unit circle where we get our answers here that we include 2 pi n, because it looks like we're solving for the sine of x. So we want to include plus 2 pi n on our solutions. So go ahead, pause your video player now and answer this question. Okay, so since I have just sine of x here to the first power, what I'm going to try to do is get the sine of x to one side, everything else to the other, and see if I can isolate the sine of x. And I can here. So I'm subtracting 3 sine of x from both sides, which leaves me with 2 sine of x, divide both sides by 2, and I get this, that the sine of x is equal to the square root of 3 over 2. And if I take a look on my unit circle now, that occurs at 2 locations. In the first quadrant, we get it at pi over 3. So pi over 3, we're at the square root, the square root of 3 over 2. And then also in the second quadrant, where our y coordinates are still positive there for the sine, we get it at 2 pi over 3. Now, we also want to include a solution every time we go around the circle here. So you notice we're including this 2 pi n or 2n pi, either way you want to write it, plus 2 pi n, because every time we come around the circle, we're going to hit that solution again. And again, now let's go back to another verifying a trig identity here. So let's go ahead and verify this. And again, I'm going to work the left side, simplifying it down until I get it to become the cosecant of x. So go ahead and give this one a shot. And so this is another way of organizing it. In the last one, I just took this left side and came straight down, simplifying along the way. That's actually the way that I prefer to do this. But this is another way. We can just say, okay, I'm going to work on the left side here. And I'm working on the left side, and I'm going to work my way down and show that it's equal to the cosecant of x. So that's another way to organize it. Okay, so the first thing I do is change everything to sine and cosine. Writing this first one, cosine of x, as a fraction over 1, since I'm going to multiply it here. So when I multiply these together, I'm going to get cosine squared of x over sine of x. This is still the sine of x right there. And what I'm doing now is I'm going to multiply by sine of x over sine of x to get a common denominator here so I can add these fractions together. I'm trying to add these fractions together because notice we have just one term over here on the right, so we want to take and combine these two terms on the left. So multiplying the top and the bottom by sine of x gives me sine squared of x over sine of x. Now I have a common denominator, I can add it together. So cosine squared plus sine squared over sine of x, and of course cosine squared plus sine squared is 1. So I'm left with 1 over sine of x, which is equal to the cosecant of x. Okay, taking a look here at question 4. Now we're going to solve an equation again. So tangent of 3x is equal to the square root of 3 over 3. So the first thing we want to do here is think about what value, what mystery value there gives us the square root of 3 over 3 when we evaluate the tangent of that angle. Once we get that, then we want to take that angle and set up our little mini equation where we have 3x is equal to whatever angle that is, plus pi n, because the period of the tangent is pi. So just a little hint there on how to do this one. So we're solving for multiple angles here. Let's go ahead and give this one a shot. So as discussed, we're saying, all right, what mystery angle, tangent of what angle will give us this square root of 3 over 3? And if you have the tangent memorized for the first quadrant, which is always a good idea, then you would know that's pi over 6. If you didn't know that, you can just take a look at the tangent of pi over 6. Remember that sine right here over cosine. And if I take sine of pi over 6, it gives me 1/2. Cosine of pi over 6 gives me the square root of 3 over 2. Take this fraction, flip it, and multiply. And the 2's will divide out, and we'll get 1 over the square root of 3. Rationalize the denominator. We can see then that it's the square root of 3 over 3. So we know that this angle is pi over 6. So then what we want to do is we want to come and take this inside here and say, okay, we want 3x to be equal to pi over 6 plus n times pi, because that's the period of the tangent. And then we're going to go ahead and solve this. So I'm going to go ahead now and multiply through by 1/3. And I'll get x all by itself. And then I'll get pi over 18 plus n pi over 3. So every pi over 3, we're going to add another answer here. So there's going to be lots of answers because we want to give all the answers between 0 and 2 pi. So my first one is going to be pi over 18. My second one, when I add 1/3 to that, let's think of this in terms of 18ths because that will make it easier for me here. This is equal to 3 times 6 gives me. So I could go ahead and now find a common denominator every time I put a value of n in there. So I'm going to put 1, 2, 3, 4, 5, 6, and so on. I think it's easier just to say, hey, this is the same. N pi over 3 is the same as 6n pi over 18. All I did was take the top and the bottom and multiply by 6. So I get a common denominator here. That way when n is 1, I'll see that this will be 6, and then I'll have the 6 plus the 1 here will give me 7 pi over 18. Then when n is 2, this would be 12 pi over 18. 12 pi plus 1 pi would give me 13 pi over 18. Still going here because we haven't even got to 1 pi yet. So that was n is 2. Now n is 3. That will be 18 pi over 18 plus the 1 there would give me 19 pi over 18. When n is 4, this will be 24 pi over 18. So 24 pi plus 1 would give me 25 pi over 18. And I think you can see what the pattern here anyways. Do you see this? Every time I'm adding another 6 pi over 18. So notice here, if we added 6 pi over 18, we're going to get to 7. Then I add another 6 pi, we're going to get to 13. Add another 6, we're going to get to 19. Then 25, this next one will be 31 pi over 18. And then if I add another 6 to that, that would be 37 pi over 18, but I don't think we're going to include that solution because now notice we've gone more than 2 pi here. If this was 36 pi over 18, that'd be 2 pi exactly. So I've already gone outside of my domain here. So here's going to be my solution set. All right, let's take a look now at question 5. Here we're asked to solve this equation, and again, this is a multiple angles equation. Sine of x over 3 is equal to 1/2. And we're just looking for solutions here between 0 and 2 pi. So very similar to the last question we just did, trying to figure out sine of what angle is going to be 1/2. And from there we set up our little mini equation for multiple angles and find all of our solutions. So go ahead, pause your video player and give this one a shot. Okay, so when does the sine, at what angle is the sine going to be equal to 1/2? And that is at pi over 6. Will be our very first solution there. Pi over 6. Okay, so then we want to come over here now and say this inside x over 3 is equal to pi over 6 plus 2 pi n. 2 pi n because the period of the sine is 2 pi. Now we want to solve this equation. We're going to go through and multiply everything by 3. Think of that as 3 over 1. So I'll get x equals, well, when I divide a 3 out here, I'll get pi over 2. And then when I multiply this by 3, I'll get 6 pi n. Okay, well, first solution comes when n is 0, so that's just going to be pi over 2. And notice, as soon as I take n equals 1, I'm going to be adding 6 pi to this value. So I've gone way outside of my domain here, which was just between 0 and 2 pi. So I'm just going to get one solution here, and that is pi over 2. Okay, let's take a look at question 6 now. So we're asked to verify this identity. Notice two terms here, one term here. So potential strategy here is to combine these two terms together like we did in the last one. Doesn't look like we have a common denominator or anything like that, but anyways, take a look at that. Also, I noticed that there's a sign of x in each of these, so another strategy might be to try to factor a sign of x out of each of those. So go ahead now and pause your video player and work on this one for a little bit and see if you can get it, and hit play when you're done. So it looked like combining the two terms was not a strategy here, or at least not the strategy that I used. I used this factoring a sign of x out. So if we factor a sign of x out front, then I get this statement 1 minus cosine squared. Well, 1 minus cosine squared is sine squared. That's a really common technique here as we're verifying trig identities. So 1 minus cosine squared is sine squared, and then of course we can take sine times sine squared of x to give us sine cubed of x to verify that identity. All right, let's take a look at question 7 now. Notice in question 7, this one is just crying out to be factored because we have a nice squared term here, then we have a nice first power term, and then a constant term at the end. So we're definitely going to want to try to factor this one. So go ahead and factor this one out and get your solutions, and make sure you find all the solutions between 0 and 2 pi here. Okay, so as discussed, we're going to factor this guy out. And it factors into 2 sine of x minus 1, sine of x minus 1. So then we get these statements. We solve these little mini equations here, set them equal to 0 and solve them. We get sine of x is 1/2, sine of x is 1. Well, the spot where sine of x is going to be 1/2, it's going to have two spots on the unit circle. Pi over 6 and then 5 pi over 6 are the two spots for the sine of x equal to 1/2. And then where the sine of x is equal to 1, that's just one location. That's going to be at pi over 2. So then our solution set will be all three of these, pi over 6, pi over 2, and 5 pi over 6. If you didn't write these in ascending order, that's okay. As long as you have the three values there, that's fine. Okay, we're going to try verifying another one here. Notice one big term on the left, two terms on the right. Again, we're going to be working this left side. So I think a strategy here might be to split this fraction up so that we get 2 there. Go ahead and give that a shot. Okay, so as discussed, we're going to split this fraction up here. So this will be 1 over sine theta, and then cosine over sine theta, and 1 over sine theta is the cosecant, cosine over sine is a cotangent, and we verified the identity. All right, taking a look at question 9, we're going to solve this equation here. Sine of x tangent of x is equal to sine of x. Ignore this little symbol there, that's just a typo. We're just looking for solutions again between 0 and 2 pi. I think this is another one where we're going to want to factor to do this. So I would get this sine of x over here and then factor this guy out to find your solutions. So go ahead, pause your video player now and give this one a shot. Okay, so as discussed, first thing we want to do is get sine of x to the left side. So we'll subtract sine of x from both sides. And then notice each of these terms will have a sine of x in it, so we're going to factor that sine of x out front. Once we get these factored, we're all set up to find our solutions. When would this equal to 0? Sine of x equal to 0. When would tangent of x minus 1 be equal to 0? So when does the sine of x equal 0? That's in two locations. That's at 0 and at pi. So those are the two spots where sine of x is equal to 0. When is the tangent of x equal to 1? Well, the tangent of x is equal to 1 where the sine and the cosine are both the same value, which is 1 in the first quadrant at pi over 4, and then again in the third quadrant where they're both negative there, and that's going to be at 5 pi over 4, where they'd both be negative, but then a negative divided by a negative would make it positive 1. So those are our two locations for the tangent. And so our solutions here are 0, pi over 4, pi, and 5 pi over 4. Okay, question 10. We're asked to verify this trig identity, and notice two terms on the left, one on the right. So I think this is a case where we're going to want to get a common denominator, try to combine these guys together. Go ahead, pause your video player and give this one a shot. Okay, let's take a look here. So first thing we're doing is getting a common denominator. The common denominator would be this multiplied by that. So we're going to take this fraction, multiply the top and the bottom by sine of x. We're going to take this fraction, multiply the top and the bottom by 1 plus cosine of x. So in the denominator, we're going to leave that factored. So those denominators will be 1 plus cosine of x times sine of x. Always a good idea to leave the denominator factored. In the numerator, we want to multiply it out. So when we multiply this guy out, we'll get 1 plus cosine x squared, which we'll multiply out in just a second here. And then here, we're going to get sine squared of x. Once we have a common denominator, now I can add those two things together. Before I add this numerator together, I got to square this guy out. So we square that guy out, we get 1 plus 2 cosine of x plus cosine squared of x. Okay. Now notice we've got this sine squared and this cosine squared of x. Anytime we see that, we want to bring those together because they're going to add up to be 1, and maybe that will potentially lead us to the path of verifying this. So you can see me here bringing the sine squared and the cosine squared together so that they add up to 1. I'm just bringing the rest of the stuff along for the ride. So let's see, now I'm going to add these two together, so I'll get 2 plus 2 cosine of x. And remember, we're headed for this 2 cosecant of x, so we got to try to simplify this guy, and we've done something like this before. The key here is to see that we can factor this out. Notice there is a common factor of 2 in each of these. We wouldn't know at this point whether it's going to go anywhere or not, but we at least want to factor that 2 out front. So you can see me here factoring that 2 out front. Once we factor the 2 out front, it's obvious that that was a good choice, because notice we have this 1 plus cosine of x and 1 plus cosine of x. Those will divide out, and leaving with 2 over sine of x. Well, 2 over sine of x is just 2 cosecant of x, which is what we were trying to show. So a lot of times you're doing these things, you don't know exactly if it's going to go anywhere, but you just kind of go for it and see what happens. If it doesn't work, then you go back and start over and try something else. Okay, last equation we're going to solve here. And so this one starts out, it doesn't look very tricky at all. So really we just, we've got just a cosine squared of x here. We're going to want to isolate that cosine of x to solve this problem. Only difference here is that when we get to our solution, we're not going to be a value we know on the unit circle. So we are going to have to use the inverse cosine to find a solution. Once we find that first solution, then we want to go back to our unit circle and find any other solutions that are going to occur between this 0 and 2 pi. So when you get to your cosine of x is equal to something here, you're not going to recognize it, so you're going to have to use inverse cosine to find it. So go ahead, pause your video player now and give this a shot. Okay, so first thing we're going to do is add 3 to both sides. 3 is equal to the 5 cosine squared of x, divide by 5. And then we're going to get 3/5 is equal to cosine squared of x. So now we want to take the square root of both sides. So we're going to get plus or minus, anytime we take the square root of something, 3/5 is equal to the cosine of x. So what we want to do now is we want to use our calculator first for the positive square root of 3/5, and then again for the negative square root of 3/5, find the inverse cosine of each of those to find our solution here. Okay, so I've set 2 equations up here now. We want to know when the cosine of x is going to be equal to positive 3/5, and when will the cosine of x be equal to the square root of negative 3/5. Sorry, square root of positive 3/5, square root of negative 3/5. I'm going to get an approximation for this square root of 3/5 in both of these cases, because I think that's going to help me figure out all of my answers on the unit circle. So 3 divided by 5.6, we're going to take the square root of that. So really this is here, this one is 0.7746, and this would be negative 0.7746. I think this is just going to help, again, find all the locations on our unit circle. Okay, because here's what I have. If I think about the cosine of x on my unit circle and when it would be equal to positive 0.7746. This is almost positive 1, right? This value right here is almost positive 1. Here is where my x-coordinate is 1 exactly. So I'm going to have two locations, one here and one here. So I need to find both angles for this one and that one to solve this equation. Looking over at this side here, where this guy is going to be equal to almost negative 1, well, that's going to be right here and right here. Again, x-coordinate of negative 1 is right there, so we're going to be a little short of that on each side. So it looks like we're going to have 4 locations here for answers. So now I want to find this first angle right here. So I'm going to find this first angle measure here, which we're going to call x. That's the angle we have there. So this angle x right there. All I have to do to find that is take the inverse cosine of this. So I still have that number, not rounded, but the actual number in my calculator. So now I'm going to take the inverse cosine of that, and it's going to tell me in radians that that first angle measure here, my first angle measure, is 0.6847. Now I want to figure out how to get to this second location here. And the way that I'm going to do that, and now remember that second location between 0 and 2 pi, if I didn't have that restriction, I could just go down here negative this angle amount and I'd be right at that location. But my answer has to be between 0 and 2 pi. So what I'm going to do for this next location is I'm going to go all the way around the circle, which would be 2 pi. Then I'm going to go back this little distance right there. That would get me to this other location here, right? So I'm going to do this 2 pi, which took me all the way around the circle, and then back this little distance. Well, that little distance is this angle right there. So 2 pi minus this guy will give me my second location for that solution. So let's see. I've got this answer in my calculator here, so I'll just make it negative and add it to 2 pi. The perfect approximation. Again, these are just approximations. I should change both of these to an approximation here. So this is 6.215, and let's change this to an approximation there again. Okay, so there are my two angle measures, and I get those angle measures from looking at my unit circle. So this is the tricky part, and I assume probably some of us weren't quite able to get this. So let's look over here at this guy now and see if you didn't get these first two. Let's stop again and try to get these second two. So what we're trying to do is we're trying to find these angle locations, right? This would be my first angle location to there, which we're calling x. And then I want to find my second angle location, which comes all the way down to here, for my second value of x there. So this first angle x will come straight from taking the inverse cosine of this negative. That's an approximation sign. This negative value there, right? We take the inverse cosine. It's going to give us that angle measure, because remember, the cosine is defined between 0 and pi. The inverse cosine is defined between 0 and pi. So that will give us this one here. Then we're going to want to do some thinking about how to get to this location there. So go ahead, if you haven't got this right, go ahead and finish this second part then. Okay, so we've got this 0.7746, which is negative. And I want to take the inverse cosine of that. I want to make sure I'm in radians. And so it gives me this as an angle measure there. And again, this is an approximation for my angle measure. It's 2.457. And that makes sense, because if I went all the way around the circle to here, that would be pi. That'd be 3.14. So I'm a little short of that. So what I want to do now is I want to get to this next spot here. Let's see. The way I'm thinking about it is if I took pi and then added this distance right there, added that little distance onto it right there, that would help me get to that location. Yes, another way to get to that location would be to take this angle right here and add pi to it. That would bring me around over to this side here. That would bring me all the way around to that location there. So two ways to do it. I think since I'm working over here, I'll just use these values. So if I want to find this little distance right here, let's use a little red mark. If I want to find just this distance right here, the way I'm going to do that is I'm going to take pi, this whole thing, and then subtract this angle right here. This angle is 2.457. Subtract that angle from pi. That will give me that little red distance. Once I have that little red distance, I can take pi and add that little red distance to get to this location. So first thing I'm going to do is I'm going to take pi minus 2.457. When I do that, I get this 0.6847, which is just what I had over here, just like I talked about. So that's that distance, same distance we had here. This distance and this distance are the same. So in fact, I already had that distance. I didn't have to do this calculation. But I've done that calculation. It tells me that it's 0.6847. Now what I want to do is to get to this spot, I want to take pi plus that 0.6847. So now I'm going to add pi to that. And so the second angle then is going to be 3.826.